All right, geometric sequences. Similar to arithmetic, this is a common sequence that is easy to work with. So we can find its S sub n formula with a clever trick. And just in general, we can analyze it pretty easily. So a geometric sequence, you've got the first term, a sub 1. Then the second term, you just multiply a sub 1 by some number r. Then the third term, you just multiply by r again, so you get r squared. Then just multiply by r again. Okay? This r is called the common ratio because, like, if you take a sub n plus 1 divided by a sub n, you get r, right? R a1 divided by a1 is r. R squared a1 divided by r a1 is r. R cubed a1 divided by r squared a1 is r. In other words, you're multiplying by r each time. That is a geometric sequence. So let's say we have r is equal to 2, and we start our a1, we say, is 5. Then the second term would be 10, the third term would be 20, the fourth term would be 40, 80, etc. You're multiplying by 2 each time. That's a geometric sequence. Okay, so what is the a sub n, the general formula for a geometric sequence? Well, we can reason that. So a sub n, we have our common ratio that we're multiplying by each time. So let's say that n starts at 1. Okay, then what you want to do is, since we're starting at 1, the first term there is no r, so raise this to the n minus 1 power. So when n is equal to 1, this is r to the 0, this goes to 1, and then you multiply by your first term. So now when n is equal to 1, a sub n is equal to a1, or a sub 1 is equal to a1. A sub 2, you get r to the 1 power times a sub 1. N is equal to 3, r squared times a sub 1, and so on. Okay? And you can also see that, let's say that the r happens to be the same as a1. So like, for example, r is 2 here. What if we started at 2 as well? Then you would have a1 to the n minus 1 times a1. You could use the exponent properties and say, and add n minus 1 plus 1. So it would simplify to a1 to the n power. A1 to the 1, a sub 1 is a1 to the 1, a1. A sub 2 is a1 squared. Okay, so what about a recursive formula? Just in general, so we're not talking about if r is equal to a1, just in general. So, okay, so we can reason this, that we know that, so r, as we talked about earlier, is equal to a sub n over a sub n minus 1. Okay, what else? What else can we say about a geometric sequence? What about the S sub n formula? So again, so S sub n, it's like you take the original sequence. This is an a sub n. The sum of the first term is 5. Sum of the first 2 terms, 15. Sum of the first 3 terms, 35. Sum of the first 4 terms, and so on. This is another sequence, and we call this S sub n. It's related to an a sub n. So like we did with an arithmetic sequence, can we use we could, for a lot of S sub n's, you can prove that they are a legitimate S of n for a sequence using the mathematical induction, but like with an arithmetic sequence, geometric sequences are pretty simple or relatively simple to other sequences, so we can use a clever trick to find S of n. So how can we do this? Let's start out by writing out S of n for a geometric sequence in general. So just for n, the sum of the first n terms. So a1 plus ra1 plus r squared a2. Oh, no. It's always a1 plus, okay, then the nth term would be r to the n a1, okay? But now what we're going to do here is say we're going to write out what is r times S of n. So r a1 plus r squared a1 plus r cubed a1 plus, and then r to the n plus 1 a1. And actually, wait, I messed this up here. This wouldn't be r to the n, because like this is r1. This is the second term though, right? This is r to the 1 power, but this is the second term. So this is r to the n minus 1 a1. And then this is r to the n a1, n minus 1 plus 1. Okay, and now what we want to do is subtract these two equations. So we've got S of n minus r S of n is equal to, so subtracting these two, we've got a1 minus r times a1 plus r a1 minus r squared a1 plus r squared a1 minus r cubed a1 plus r to the n minus 1 a1 plus r to the n a1. Okay, so now what happens is, if you look, like if you just took out, you can just take off all of these parentheses, right? Because you're just adding, you're adding each time. And this and this sum to 0. This and this sum to 0, you see? And I should have put this is plus, right? So with this simplification, this comes out to S of n minus r S of n. You just get a1. Oh, wait, and then I messed this up. This is minus. You're subtracting these two. Yeah. So all these middle terms go away, and you're just left with a sub 1 minus r to the n times a sub 1. Okay? And so now just solve for s sub n. So let's factor out an s sub n here. Okay, and then let's take out an a sub 1. So we get a sub 1, 1 minus okay? So that is, if you have a geometric sequence and you want to find the sum of the first 100 terms or whatever, you can just plug it into this formula. Okay, so now what else about geometric sequences? The limit of a geometric sequence. So the limit of a sub n, or even the limit of s sub n. What about a geometric series? So we'll go into more detail on geometric series and evaluating them in later videos. But so okay, the limit of a geometric sequence. The limit of a geometric sequence. So that could go from the limit as n approaches infinity or negative infinity, but we're going to just evaluate it going to just infinity. So what is the limit as n approaches infinity of this a sub n? This is for the formula for a sequence, the geometric sequence. Well, the idea is if r is, or the absolute value of r is less than 1, then this will go to 0. Right? Because if you keep multiplying a number that's less than 1, the absolute value is less than 1 by itself an infinite number of times, it gets tiny, right? So you're getting an infinitesimally small number times this finite number a1. That's approaching 0. Okay, so the limit of the sequence of a geometric sequence converges to 0. Okay, now what about the limit as n approaches infinity of s sub n, which would be the evaluating the geometric series? Okay. Well, in a similar way, if the absolute value of r is less than 1, so if the absolute value of r is greater than 1, then this limit goes to infinity. It doesn't converge. And similarly, well, if it's equal to 1, if r is equal to 1, then you're just multiplying a1 times 1 over and over again. So that limit, the limit as n approaches infinity of a sub n, when r is equal to 1, is a sub 1. The sum of an infinite number of a sub 1s goes to infinity. If absolute value of r is greater than 1, then you're multiplying it a sub 1 by bigger and bigger numbers. So that limit of a sub n goes to infinity. That limit of s sub n goes to infinity. But what about the limit of s sub n as n goes to infinity of s sub n when the absolute value of r is less than 1? In that case, this r to the n goes to 0, right? So you end up getting a sub 1 times 1 minus 0. This converges to this value, right? Because again, and it's the same idea. This limit is, when r is less than 1, this limit is approaching 0. So 1 minus something that's tiny is approaching 1 times a sub 1, and then there's n's not in the denominator. So that's an interesting result. If the sum of an infinite geometric series, infinite, is actually a legitimate number, a finite number. An infinite series, an infinite number of terms converges to this. If you have a geometric series, the absolute value of r is less than 1, summing that series with an infinite number of terms converges to this value. And we'll talk about that more in the upcoming videos on series. So that is geometric sequences.